Okay, so question 60, propose a mechanism for the following reaction. So again, just like with all these other mechanism questions that we do, they can seem daunting at first, but the key is to make sure, to make sure if you hit a roadblock anywhere along the way, to make sure that don't freak out, you can always back up, try something different, okay? So this one's a slightly harder variant from the last question that we did. But again, we have the starting material, we have our reagent, and we have our product. So we have a general idea of what's going to happen. All we have to do is describe the road, describe the path, how to get from A to B. So tell me a story, basically. Um, so let's go ahead and start with, I'll redraw the molecule down below. And one thing that I would definitely always encourage you to do is, if it looks like it might be a more complicated mechanism, is to number and or letter all of your carbons, because it's going to be really easy to get lost along the path to get from part A or point A to point B. Okay, especially whenever you have something crazy going on, like obviously we're starting with a five-membered ring and we're doing a what seems to be a ring expansion to a six-membered ring. I would always recommend just start off by trying to do labeling of all of your carbons. Okay, so what I'm going to do is just number these guys 1, 2, 3, 4, 5, 6, 7, 8. And again, my specific numbering is not unique. This isn't a right way to number. You can number however you want. As long as you are consistent, that's what's important. Okay? So we've numbered our carbons, and we're going to go ahead and start trying to do the mechanism. So the setup is going to be very simple. Again, you have to draw on your experience of the context of what we've been talking about. So in class, everything has been framed in the context of alkenes acting as nucleophiles and or bases. And so again, the reagents should hint that you need to do some kind of acid-catalyzed hydration. And indeed, it looks like we are doing an acid-catalyzed hydration. So again, we're starting with the alkene, and we're shifting to an alkane, and we're adding a hydroxyl group. So it looks like we're definitely doing an acid-catalyzed hydration. It's just there's something else extra going on that's causing this funky shift. Okay, so let's just go ahead and start the problem under the premise that we're going to do an acid catalyzed hydration. So let's go ahead and add our acid. So I'm just going to go ahead and add H+. So you could write out the sulfuric acid if you want. It's a lot more simple in my mind to just write out H+, because that's what's really of interest here. That's what's going to help you out. Okay, so let's go ahead and do our acid-base reaction. We're going to use our alkene, or the pi electrons on the alkene, to attack our H+. And so let's go ahead and show the product from that. So we're going to have, just going to copy and paste this guy, actually. So we have our alkene reacting with the acid. So I'm going to go ahead and get rid of this double bond. And now we have to choose where we're going to form our carbocation. So that's another bit. You have to remember that the intermediate of an acid-catalyzed hydration is a carbocation. So you have to ask yourself, where do we want to put the C+? On the 2 or on the 1? Well, you should try to categorize which would be more stable. If we put the carbocation on 2, we would get a secondary carbocation, which is pretty stable, versus if we put it on 1, we would get a primary carbocation, which is less stable. So of the two, I would choose to put the carbocation on carbon 2. Okay, so let's just go forward under that premise. Again, I could be right, I could be wrong. It just depends on if it turns out whether or not if I'm going in the right direction or not. If I go in the wrong direction, I'll reverse it and try something different. Okay, so good thing for me is that I get to copy paste. Unfortunately, whenever you're taking an exam or taking a quiz, it is important to draw out each intermediate along the way. Because again, you have to pretend like I have no idea what's going on in your head, and you have to tell me a story. And a very smooth story is going to go a long way to being more acceptable than a kind of haphazard, choppy story. So make sure you are clear in all of the bond making and bond breaking that you do. Okay, anyway, slight tangent. But now, so we know that obviously we could do, if we were doing a classical acid catalyzed hydration, what we would do is we would take that water and we would attack that carbocation, okay? And then we'd get a hydration on carbon 2. That's obviously not what has happened here. So we have to now deviate from that classical method for how we do an acid catalyzed hydration. So something else funky is going on here. So now we have to start improvising. We have to do something different. So now we know that we need to go from a 5-membered ring to a 6-membered ring. So let's see, how can we do that? Well, we could try to do a ring expansion, or we could do a methyl shift, or we could do a hydride shift. If we do a methyl shift from here to here, from 8 to 2, that would be one possibility. But if we did that, we would get this kind of structure, where we would have our overall ring system still confined to a 5-membered ring. Okay, so we would definitely, do our shift, and it would end up looking something like this. Something like this, where we have our carbocation now on carbon 3, and carbon 8 would be here, carbon 2 would be here. Okay, so now we've done our carbocation or our methyl shift, which would definitely stabilize this guy. This would now be a tertiary carbocation versus being a secondary, but that doesn't really help us get to the product. Okay, so this is one method that you could possibly do, but it's actually not going to be very helpful. So let's stop, backtrack, try something else. Okay, so that's not going to work. So let's try something else. So instead of doing a methyl shift, let's try to do a ring expansion. So if we do a ring expansion, we can either break the 7 to 3 bond, or we can break the 3 to 4 bond. It doesn't really matter in my mind either way. But let's just go ahead and break the 3-4 bond just because it's simpler to draw. Okay, so let's go ahead and do that. We'll break that bond. And basically what you're saying here is that you are breaking the 3-4 bond and you're remaking a new bond. Okay, either between carbon 3 and carbon 2, or between carbon 4 and carbon 2. Again, we don't really want to make an alkene, which would happen between carbon 3 and carbon 2, because that's not what we would get in the end of the day. Okay, so what we really want to do is we want to expand that ring, make it a 6-membered ring, which means we need to make a new bond between 4 and 2. Okay, so I'll just go ahead and redraw this guy as if it was a 6-membered ring. So 1, 2, 3, 4, 5, 6. Okay, so now the question then is, what is what? Everything has been rearranged, which again is a good way. Now, this isn't going to be as big of a deal because we have all of our carbons numbered. Okay, so let's just start off on the ring. So we know the ring's going to have 7, 6, 5, and 4 in it. So let's just start over that way. Okay, so let's keep this carbon 7, 6, 5, 4. And we know now that we formed a new bond between 4 and 2. So let's go ahead and put 2 here. And 2 is attached to 3, so go ahead and put 3 here. And 8 is attached to 3, so let's go ahead and put 8 up here. Okay, so we'll put 8 up here. And now we're also missing carbons, or just one more carbon, we're missing carbon 1. And so that we know that carbon 1 is still attached to 2, so we'll go ahead and add that here. So go ahead and add carbon 1 up here. And so now we've taken care of every single one of our carbons and methyl groups. So overall, 8 carbons on the left. Overall, 8 carbons on the right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now the big issue is, where are we going to actually put our carbocation? Because again, charge balance, we have a positive on the left. We have to have a positive somewhere on the right. And so now this is very important for you to be able to recognize implicit hydrogens, where they are and where they are not. Okay, so with carbon 8, we know we have 3 different carbons attached, or 3 different hydrogens attached. 1, 2, 3. So 3 attached here. So we know our H plus or our C plus isn't there. 1, 2, 3. Okay, so you should actually start looking around the area where you're making bonds and breaking bonds. So thinking back to carbon 2 only had 1 to begin with. It still only had 1 even when it was this carbocation. And so now carbon 2 should still have that hydrogen there. So now thinking back to this intermediate where carbon 2 is charged, carbon 2 now has 1, 2, 3, 4 bonds to it. So carbon 2 is neutral. Okay, so that leaves either carbon 1, which we really didn't affect, so we're going to kind of ignore it, and carbon 3. So carbon 3 is a prime candidate for being carbocation. So now let's think about how many hydrogens were attached to carbon 3 before we moved on. So 1, 2, 3, 4 bonds to 3. So that means that there are no hydrogens that are implicit. So thinking back to this now, carbon 3. Now, since we have no implicit hydrogens, that means that there are only 1, 2, 3 bonds attached to carbon 3, which means that overall, if we did a valence charge or a charge calculation, carbon 3 would have overall valence of 4 minus 1, 2, 3 bonds minus 0 lone pairs. So it's going to be overall positively charged right there. Okay, so that's where our positive charge is. And just kind of as an aside, if you look at what we're going for versus what we have, it looks quite similar. Okay, so now all we have to do is recognize here we have hydrogen, and recognize here we have CH3 and CH3. Okay, so we have 2 CH3s, one here and one here, so this would be carbon 3, this would be carbon 2. So now all we have to do is add on this hydroxyl bit, and we're pretty much done. So let's go ahead and throw in our water. So this is going back to, we're no longer improvising, we're more so kind of floating along with the classical method of showing a hydration or an acid catalyzed hydration. So this is kind of the end game. So the beginning game, just like in chess, is very predictable. The end game, just like in chess, can be quite predictable. Everything in between can be a little bit murky, a little bit up for grabs. That's why it's more like improv. So now this is actually quite simple. We're basically going back now to our nucleophile electrophile definition. This is going to be our nucleophile. This is going to be our electrophile. We're going to have a bond forming process here, so going for the electrons on the oxygen attacking this electrophilic carbocation. And so now after that, we're going to redraw our molecule. I'm going to draw my little portal arrows here. So going back down to this way, we have our portal arrow, redraw the molecule overall. So let's redraw this guy. So I'm going to get rid of this. I'm going to get rid of these implicit hydrogens just to make it a little bit prettier. Okay. And we've already formed our carbon-oxygen bond above, so I'm just going to go ahead and draw that out. So we have our carbon-oxygen bond, but now we have to take care of the fact that this oxygen is positively charged. Okay, we know that by formal charge calculation. We also know that just by looking at it, oxygen with 3 bonds is going to be positively charged. So looking back at our final product, the oxygen is neutral. So how do we get the oxygen to become neutral? Well, we have an excess of water in solution, so let's take a little bit of water. I'm going to take this, have it act as a base, and it's going to remove that excess proton. We're going to put the electrons that used to be used for this formal bond onto this oxygen as a lone pair. Okay, so now we'll redraw this, and we'll get our final product, and it actually will be very nice. I'm going to get rid of these arrows, and again, we broke that oxygen-hydrogen bond, and we used those electrons to form that lone pair on the oxygen to make it neutral. Okay, so overall, this was a 1, 2, 3, 4-step mechanism. The only step that was kind of improv was going from the second to the third structure. Everything other than that was extremely classical acid catalyzed hydration. First step was classical acid catalyzed hydration, and so this was first, second, third. Third step was classic acid catalyzed hydration, and the fourth step was classic acid catalyzed hydration. So the only weird bit was this right here. Okay, everything else was extremely predictable. Okay, and again, this might not be obvious at the very beginning. It takes practice. So just there are multiple other questions like this in your book, as well as on electronic lectures if those are available. So go ahead and practice, practice, practice. Get used to the electrophile nucleophile concept, as well as getting used to how electrons can move around. Okay, all right, I think that's it for this chapter.